Okay, can you hear me and can you see my screen? Great. So this is a walkthrough for a Linux kernel bug we've had some time ago in one of the drivers, and it's a really nice bug. It's very simple, and it bypasses all the Intel CPU protections such as SMEP and SMAP, or if you're on the ARM architecture, PXN and PAN. And the bug is related to using syscalls in the kernel. So syscalls provided to user space. For example, something like say opening a file and getting a file descriptor using the open syscall, and then writing into that file descriptor using the write syscall. And you can do that. You can use syscalls in the kernel. If you just Google how to use syscalls in the kernel, you'll get a few blogs by some people explaining what you should do. Ironically, I think this would be your first page of results on Google. There'll be a post by I think either Keith or Greg saying you should never do this in the kernel. And the title of that post was things you should never do in the kernel, or something like that. But driver developers, especially new driver developers, they tend to use this functionality in the kernel, I guess because they're already familiar with the user space Linux syscalls, and when it comes down to implementing something like writing to a file from kernel space, that's what they use. And I think this bug is somewhat common, maybe not in the official kernel repository, but in some custom drivers for mobile platforms or embedded systems. Project Zero had a bug related to this recently, I think last year, late last year. It was in a driver for some mobile platform. So what I've done is, well, what I'll do is I'll go from the description of the bug to the actual exploitation. And before I do that, I'll just show you my setup and what I've done so far. If there are any questions, you can just post them here. I'll be reading the comments. So what I've got is my test VM that's running 4.6.1 kernel. It doesn't really matter, it's just the kernel I had compiled. And I've got my debugger attached to the kernel. I don't really need a debugger to exploit this particular bug or a class of bugs, but it's there just to show you how this is working and what data structures are being used internally. And what I've done is I've created this sample module that basically mimics the vulnerable driver that I had. The bug was actually in the compat ioctl, in the 32-bit ioctl, but it doesn't matter, we'll be using the just standard 64-bit ioctls. Just makes it easier. And there were actually two bugs. So the first one was related to the address limit, and the second bug was just a standard information leak, a stack information leak. So I guess I'm not going to explain the information leak. It's pretty straightforward. Let's just say there was a structure that was allocated on the kernel stack, so something like some struct kptr. So this is the definition of that structure. It's got three members, 364-bit integers, address 1, 2, and 3. And then we set address 1 and address 3, skipping address 2. And before returning, we copy that structure on the kernel stack back to user space. So potentially leaking address 2, or whatever was at address 2, 8 bytes. And align stack is it's just something I did to just to make sure that when I copy that structure back to user space, address 2 will point to something useful. And in my case, it's pointing to it's a pointer to a variable on the stack, right? So obviously in the original code there was no intentional stack alignment, but it just happened that when that structure was copied back to user space, that member, the uninitialized member of the structure, was was a pointer to a variable on the stack. So it contained the address of a variable on the stack. Okay. So yeah, for now let's just assume there's this information leak, a stack information leak, and it's working. So before I explain the bug, the address limit bug, who doesn't know what thread info structure is and address limit in that structure? Yeah, maybe you should start looking for another job then. Okay, so there's a thread info structure, struct thread info, allocated for every process on the system. This structure is located on the stack, obviously on the kernel stack, and it's at the base of the kernel stack. Yeah, for every single user space process. So I can actually show you that. Alright, so the first member of that structure is the pointer to the task structure, and then we've got this address limit member. And by default, when your process is running in user space, the address limit is set to the highest virtual memory address belonging to user space. So there is this separation between the kernel and user space, and address limit is pointing to the highest address in user space. So anything below address limit is user space, anything above address limit is kernel space, generally speaking. Yeah. So that's the address limit, and every function that's copying data to and from the kernel. So functions like copy to user, copy from user, get user, put user, string copy from user, etc. They use address limit. So they're checking address limit to make sure that the pointer that you're passing belongs to kernel space or user space. So for example, let's take copy to user. The first argument of that function is the destination. Right? So you're copying data back to user space. So that should be a user space pointer. And if you try to pass a kernel space pointer instead of the user space pointer, copy to user will check that address. It will check, is this address greater than address limit? If it is greater than address limit, then that's an error, because that address is not in user space, it's in kernel space. And it will just return an error. Otherwise, it's in user space and it performs the copy operation. Yeah, all functions that sort of transfer data to and from the kernel, they perform this check using the address limit. Well, you can't do that. You can't. Well, obviously, if you say in the kernel and you've got the highest privilege level, you can dereference any memory address, any virtual memory address, be it in kernel space or user space. But if you do that, if you dereference a user space address while being in the kernel, and you dereference it directly, so either by writing into that address or reading from that address, you'd be introducing vulnerabilities. And that's why these functions are there. So copy to user, copy from user, get user, put user. That's how you move data to and from the kernel. So you shouldn't be using addresses directly. Okay. So that's the idea behind this address limit. So going back to the bug. So the bug is in this ioctl. The log starts ioctl, and in the original code, this ioctl was logging some driver statistics, and it was opening a file on the file system and then writing into that file. So that's what log starts does. Basically, there's this getFD function, helper function that gets the file descriptor. And the way it gets the file descriptor is just by using the open syscall. So very similar to user space. The first argument is the file name, then flags, etc. So then it's checking that the open syscall worked. If it worked, then you get a valid file descriptor and you just return that file descriptor here. Otherwise, you return this invalid value. So we get back to here, and again we check the returned a value. If it's a valid file descriptor, we just take that file descriptor and we write into that file descriptor 5 bytes using the write syscall, and then just return the number of bytes. Otherwise, we just return this invalid value. So this pretty much looks like user space. Opening a file descriptor, then writing to a file descriptor, except maybe for getFS and setFS functions. They're actually macro definitions. But what they do is they manipulate the address limit for the current process. Right? If you just skip that, so if I do something like this, right, I recompile my module, load it, and call this ioctl log starts, it's going to fail. So it's not going to write to a file because the syscall, let's say sysopen, would fail because of the address limit being the user data segment, not the kernel data segment. Okay, so the question, why does it fail? Let's take an example. So let's take a sysopen, right? The open syscall. And normally you would call this syscall from user space. The first argument is the file name. And in our case, file name is this log file, right? TMP starts. And that file name, it's a pointer to a character buffer, right? And if you call that syscall from user space, that pointer would be a user space pointer because it's in user space. But in our case, it's not. It's in kernel space, log file. And when you try to call this syscall, what it will do is eventually down the execution path, it will use one of the functions like copy from user or string copy from user to copy this file name to some local kernel variable, either on the stack or allocated on the heap. And when it does that, the copy operation would fail because the address limit is set to the user data segment, to the user to the highest address that belongs to user space. But log file is pointing to a kernel memory address. So it will say, is the address greater than the address limit? Yes. Okay, that's an error. Does that explain it? Okay, let's do an example. So let's take the open syscall. Should be in the file system. Okay, open. Okay, so this is the implementation of the open syscall, and then we call this do sysopen. Okay, so file name is the user space pointer. Well, it's supposed to be the user space pointer. So we take the file name and we use it here. So get name, file name. Okay, so it's get name flags. So get name flags, and again, the first argument is the file name, the user space pointer. So again, we take that file name and okay, so down here. So as I said, it would do some copy operations like copy from user or string copy from user in this case. So it's copying the file name into some local kernel variable kname. Right, because as I said, you cannot use memory user space addresses directly. You have to copy data back to kernel space before you can process it. Right, so that's what's happening here. So it's copying file name to kname, and if we look at the implementation of string copy from user, string copy from user. So that would be 15. Okay, so that's string copy from user. And what we do here is, so source is our file name, it's a user space pointer, and destination is the kernel address. Okay, so here we perform the check if the source address is less than the max address. And the source address is our file name, the user space pointer, and max address is user address max. x86. So it's just a macro definition that basically returns the address limit for the current process. Right. So what we're doing here is we're checking that the source address is less than the address limit for the current process. If it's less than the address limit, then it's a user space address. If it's greater than, it's a kernel space address. Right. So in our case, because this is a kernel space pointer, it'll get to this check and say, is this kernel space pointer less than the maximum user space address? No, it's not. Right. So it would return a fault. But yeah, otherwise it would perform the copy operation. Does that explain it? Okay, great. So yeah, all functions. So copy from user, copy to user, get user, put user would perform a check like that. So some of them are now optimized. I mean, depending on the kernel version, I think copy to user is now implemented in assembly based on the size if it's a constant or something. But yeah, essentially it would perform this check against the address limit. Okay, so, and that's why we use these operations, these functions, getFS, setFS. So what we're doing here is setting the address limit of the current process to the kernel data segment. And the kernel data segment is defined as some very large 64-bit integer. Right, so let's say -1 converted to unsigned. And what it does is basically when you get to this check, like this one, the address limit, the max address would be some really high value, the highest value. And you would say, is this kernel pointer less than, FFFFFF in hex? It is less than that, obviously. So the check would succeed and we would perform the copy operation. Right, so that's what you do. You set the address limit to the kernel data segment, and then you can use the syscalls that expect some pointers from user space. And yeah. Okay. And the getFS operation, I think I just showed you the getFS macro. So getFS basically just returns the address limit for the current process. setFS sets that limit. And that's what we do here. So first we save the current value of the address limit. And if it's a user space process, this value would be the user data segment. Then we set this the address limit to the kernel data segment, execute the syscalls, so open a file descriptor, write into that file descriptor, and then we reset the original value of the address limit. So we set it back to the user data segment before returning to user space. So the bug is actually in the this helper function, get file descriptor, or well, it's log starts. But what happens here is, so you try to open a file and get a file descriptor. If it's an error, if it's -1, you return. So we get back to here. We check the file descriptor again. It's an error, so we return, skipping that this step here. So resetting the original value of the address limit. So what we'll do is we'll set the address limit to the kernel data segment and then return back to user space. And when we return back to user space to our process, we'll be running with the kernel data segment instead of the user data segment. And that's a big problem, because then you can just write to any kernel memory address, or you can read from any kernel memory address. So you've got arbitrary write and arbitrary read in the kernel. Yeah. Okay. So when I say you can take any memory address and write into that memory address, I don't mean that you just take. So you're in user space and you take some kernel memory address and you directly write into that address. You just get a seg fault because it's still controlled by segmentation. You would have to find a syscall or some ioctl or some path that's reachable from user space that's using one of those functions like copy to user, copy from user, get user, and then you would pass that pointer that's supposed to be, say, a user space pointer, but instead of that you would pass the kernel pointer. Right? Let's say it's copy to user. So instead of the user space pointer, you would provide the kernel space pointer and you would write something into that location in kernel space. because of the address limit. Yeah, I'll show you in a second. But many syscalls use those functions. Most syscalls use like copy to user or something like that. But I'll show you a standard way in a minute. I guess the assumption here was that you can always get a file descriptor. So this open syscall would generally succeed if you try it in user space, if you've got sufficient permissions, if you can open the file for, say, reading and writing, then you would get a file descriptor back, unless maybe you're running out of memory. So you cannot allocate some kernel data structures internally, and it fails. But there is actually a limit on the number of open file descriptors, and this limit is per process. I can actually show you that. I don't remember the exact syntax. It's not very helpful. Yeah, so there is a soft limit and there is a hard limit, and we're interested in the maximum number of open file descriptors, right? So give me the soft limit for the number of open file descriptors, and that's set to 1024. So by default, my process can open 1024 file descriptors. If I try to open more than 1024, the open syscall would fail. To be honest, I think the difference between the soft and the hard limit is that you can increase your own soft limit up to the hard limit, but you cannot increase the hard limit if this process is not a privileged process. I think, yeah, but just Google it. As I remember, if it's a non-privileged process, you can increase your soft limit, but you cannot increase the hard limit. But in our case, we are working with the soft limit. Let's just keep it 1024. And what I'll do is I'll got it open. Yeah. So the module is loaded, my sample module, and when it's loaded, it creates a character device. So dev sample, and I can just open that character device, get a file descriptor, and then perform some ioctls on that character device. Let's say open device path. And let's just check. Okay, and now I can do something like ioctl file descriptor, and my ioctl was log stats. No arguments. Okay, so now if I would compile this and run it, nothing happens, right? It goes through that execution path, so it opens the, it uses the open syscall to get the file descriptor, gets the file descriptor, writes into that file descriptor, and resets the original value of address limit, and then returns back to user space. So what we'll do instead is we'll just keep allocating opening new files, so getting new file descriptors up to that limit, the soft limit 1024, and then we'll perform this ioctl again. So at that point, because we've got the maximum number of open file descriptors, we'll get to the sysopen in the driver, and that open syscall would fail. So it was 2000. So just keep opening. Let's see, password. Well, what was greater than 0? And increment I. So what I'm doing here is basically opening, getting new file descriptors using the open syscall, and I know that I can read this file, etc password, and I just keep getting new file descriptors and incrementing I. So then I'll just print this I value. Right, so it's 1021, and the reason it's 1021 is because I've got a few file descriptors already open. I've got my standard input, output, and error, so 3 file descriptors, and then I can open 1021 more file descriptors. So at this point, when I'll get to the ioctl, it will go through the execution path. It will try to perform this open here, and it would fail. So it would return -1, and I'll get back to here returning this invalid value and skipping that setfs, oldfs step here. So I guess what I can show you is the value of the address limit after this process returns back to user space. I can set the breakpoint on this ioctl here. Okay, I would need to load the module. What I'm going to do is I'm going to use this getUID syscall, and I'll set the breakpoint on getUID. So if I'll break on getUID, I can print my current address limit value, and if it's something like -1, then I'm running with the kernel data segment. There's no reason I'm using getUID. It's just something for me to set the breakpoint. Right, I know that my process is using getUID syscall, so if I'll break at getUID, I know it's probably my process. But yeah, obviously you wouldn't use something like say a write syscall, because there are many processes on your system using write, right? So you would have many breakpoints. Okay. So what I'll do is go back to the debugger, and I'll set the breakpoint on getUID. And we'll just recompile it. Okay, we hit the breakpoint, and this is my stack value. So remember the thread infrastructure is at the base of the stack. So I'm just going to take this address and mask out the list 13 or 14 bits or whatever your stack size is. In my case, the stack size is 4000 or 16 kilobytes. And the reason it's 16 kilobytes is because I've got kernel address sanitizer enabled in this kernel. So that increases the stack size. Yeah, so the stack size that's configurable at compile time, and also the page size is configurable at compile time. So generally, if you just take sort of default configuration, then the page size is 4 kilobytes or 1000 in hex. And for the stack on a 64-bit system, you've got 2 pages, so 8 kilobytes stack size. But in my case, it's 16 kilobytes because of the address sanitizer. Yeah, this is just masking out the 4 pages, right? To get the base address of my stack. So this would be my base address. Okay. So now I know the address of the thread infrastructure. So what I'm going to do is I'll just typecast it to this thread infrastructure, and then I'll print the address limit. And you can see that the value of my address limit is this high memory address. So -1 if it was the assigned integer, long integer. Does that make sense? Yeah, so now I know that I'm running with the kernel data segment instead of the user data segment. And at this point I can write to any kernel memory address, or I can read from any kernel memory address. Okay. Right, so I'm going to remove this get UID. And as I said, you can now find a syscall that uses a copy to user function, and then pass the destination pointer to be a kernel space pointer instead of the user space pointer, and that's going to work. But instead, the standard way is to use a pipe. So if you've ever used a pipe, let's call it pipe FD. So you would allocate 2 file descriptors, so file descriptor 0 and file descriptor 1, and then for a pipe you always write into file descriptor 1 and you read from file descriptor 0. It's unidirectional, so it works only in one direction. So writing into file descriptor 1 and reading from file descriptor 0. And then you just call the pipe syscall on that. And now I've got 2 file descriptors initialized, so I can do something like, so this is what you would normally do with a pipe. You would write into file descriptor 1, let's say you're writing this value test, 4 bytes, and then you would read from file descriptor 0 into some variable. So let's say I've got some buffer, which is 4 bytes. So I would read into that buffer 4 bytes. Alright, so that's how you would normally use it. And what it does internally is this test, the character buffer, the string, it's in user space. So you're actually passing a pointer to this string. It takes that address, the pointer, reads from that location, again it's in user space, and then writes the value at that location back into this buffer. Right, so you're reading 4 bytes in this case. Yeah, so now instead of passing this, say, a user space pointer for the test character buffer, you can provide any kernel memory address. And you can read from any kernel memory address. So basically getting arbitrary read in the kernel. So something like, right, some kernel memory address. And let's say you want to read yes, a pointer size. Something like that, 8 bytes. And then it works it works the other way as well. So if you want to write into some kernel memory address, basically do the same thing, but now let's say I want to write blah. Right, so I want to write the value 0 into some kernel memory address at this location, something FFFFF, whatever. So that's how I would do it. Right, so take the address of this variable, and then read from that location, and then write the value at that location into this address. Okay, so remember I've mentioned that the address limit, the information leak ioctl, and now that's very useful because what we can do is we can get the address of the credential structure using the address, the information leak, and then write into that location. So just overwrite it with zeros. So overwrite UID, GID with zeros, and that way you just escalate your privileges. So it's not a standard return to user attack. You know the exact location of the credential structure, and then you overwrite UID and GID members of that structure with zeros. So what I'll do is let me just remove this for now. So ioctl fd there were arguments to that syscall. Yeah, okay, it's the structure itself. And let's just print the value. Address 2. Okay, so that looks like a valid address. So in my case, this would be the value of some pointer pointing to a variable on the kernel stack. Alright, so instead of using the say RSP value, like what I did in the debugger, I can just take this value, mask out the least significant 14 bits, and that would be my base address for the stack. So now I know where thread info structure is. I can just use that. Does that make sense? Okay, good. So that's what I'm going to do. I'll cite unsigned long thread info equals address 2. Alright, so now I've got the address of my thread info structure, and I can read from that location. I can read from that address, and if I read from that address, I'll get the task structure. Do you remember that? So going back to the struct thread info. So the first member of that structure is a pointer to the task structure. So if I'm reading from that address, I'm reading the value of that pointer. Okay. So I'll use the pipe. So I'll be reading from thread info, 8 bytes, and I'll be writing that into, let's say, what do we call it? Task. Let's call it task. I'll just print the value. Okay. So because we've got too many file descriptors open, the read and write syscalls would fail. Right, so what we have to do is create the pipe before we allocate those file descriptors. So let's say here. Okay, that's better. So this is the task structure, and then I can just use the offsets into that structure to read various members of that structure. And if I go back to the debugger, it's a pretty big structure. Let's see if I can find it. But there'll be a pointer to the credential structure in this structure. Right, and the credential structure contains the UID, GID, and so on. So ptype struct cred. Right, so UID, GID, effective UID, GID, etc. So that's what we want. We want the address of that credential structure. So we need to know the offset of the cred pointer within the task structure. Yeah, so I can do something like, say, like this. Let's do this. Task struct pointer, some memory address, any memory address really, doesn't matter. Okay, so we can see that the credential, the cred pointer within that structure, the task structure, is at the offset of 600 in hex. Right. So I just took some random memory location like 400,000 in hex, and then computed the offset of that credentials, cred pointer in that structure. Does that Make sense? Okay, good. So now I know it's at 600, and what I can do is I can read the value of that pointer, of my cred pointer within the task structure, and I can just get the pointer, the value of that pointer. So let's call this cred. So the address of the cred structure, and I'll read from task plus the offset, so 600 in hex, and I'll read it into that cred variable, and I'll just print. Okay, so now I've got the value of the cred pointer, so that's where the cred structure is located. And then if we look at the cred structure, struct cred, this is what we get. So the UID is at the offset of 4. So atomic T usage, atomic T is defined as a standard integer, so a 4-byte integer. So if we take the base address of the cred structure plus 4, then we're going to get UID. And KUID underscore T is also a standard integer, so 4 bytes. So if we do another plus another 4 bytes, we're going to get GID and so on. So that's what I'm going to do. I'm just going to read the value, my UID value. So let's say int UID, take the cred plus 4 and save it into UID. So UID. So my UID is 1000, so just a standard user, right? And if I'll print my GID value, so it would be plus 8. Let's call it. Alright, so it would be 1000 as well. So now I know the location of my GID and EID and effective UID, etc. So what I can do is now use the pipe again, but instead of reading values, I can overwrite those UID and GID locations. So I'm gonna remove, well, I'll keep this for now. So let's say I want to overwrite my UID with 0. So what I'll do is I'll take the address of this variable UID, and then I'll write it into this location. So I'm just swapping the destination. Right? So I'm writing the value 0 in this case into this location, so cred plus 4. So the beginning of my credential structure plus 4 bytes. And then what I'll do is I'll write it into GID as well, so plus 8. And then I'll call my the get UID syscall just to make sure that that worked, and I'm getting UID of 0. Alright, so you can see it's now 0. So what I can do now is basically just spawn a shell, and I'll get a root shell. Well, no, because if I'll try to do that, if I'll actually need to change my effective UID and GID. So what I'll do is I'll get the offset of effective UID. So this would be 4, 8, 12, 16, 18, and 20, right? So I'm going to overwrite offset 18 and then offset 20. And now I can execute my shell, and I would get a root shell. Okay, so shared libraries. Okay, this is again because I've opened too many file descriptors. Alright, so when I call this syscall system, it tries to open another file descriptor, but I've exceeded the maximum number of file descriptors. So what I should do is close a few file descriptors before I do that. So let's just do for I don't know, 1,000, 100, I don't know. Close fds I. I don't have I. No. And we get the root shell. So it's I think it's pretty straightforward, and it's a clean exit. So if I exit, no errors. I can run my exploit as many times as I like. It's not like a return to user. I'm actually I'm running out of time, and I have to go. So if there are any questions, I can you can just email me or just post them here, and I'll try to answer them later. Alright.